Hello friends, in this video we will learn how to design a belt when combination of stresses are present. So in the last video we have learned how to calculate the design stresses inside the belt using IS 800. So for stresses in a belt there are two situations. First, we can have only one kind of stresses. It can be tensile, compressive or shear in nature. Or we can have multiple stresses present. For example, we can have shear as well as tension. We can have shear as well as compression. Another possibility, we can have shear, tension as well as twisting moment is also applied in that case. So let's first discuss when we have only one stress, this is tensile, compressive or shear that is present in the belt. So how we check or how we calculate the stress inside the belt? So this is given in clause 10.5.9 and that says stresses due to individual forces when subjected to either compressive or tensile or shear forces alone. So we have only one forces. In that case, a stress inside the belt can be calculated using this formula. So this formula is P divided by T times LW, and FA is basically calculated normal stress due to the axial force, and this is in Newton per millimeter square. Now these two terms P, basically P is the force that is transmitted, and TT, as I said in the previous videos also. So this is the effective throat thickness that is often written as K times the belt size, where K is a constant that depends upon the angle between the fusion faces. And LW is the effective length of the belt, and this is in millimeter. And Q is the shear stresses in Newton per millimeter square. So when only one stress is present, either tensile, shear or compressive, we can calculate the shear stress or compressive stress or tensile stress using this formula. Now the question is, when we have multiple stresses, what we do? Similar to the previous case, in this case also, code gives recommendation for the calculation of equivalent stress in the belt. And this is given in clause 10.5.10, and this says how we calculate equivalent stress when combination of stresses are present. So this clause says when subjected to combination of normal and shear stresses, the equivalent stress F sub E shall satisfy the following equation. So this equation is basically related to the total equivalent stress that is coming due to the forces should be less than the stress of the belt. In other words, this part, that is the demand that is coming from the load, and this part is related to capacity. That is the capacity of the belt that is related to material. So we have to satisfy this inequality for a safe belt. Now let us discuss what are these terms in these equations are. So FA is basically normal stress. So this term due to compression or tension and axial forces or bending moment. So this is the normal stress generated due to compression, tension, axial forces or due to the bending action. And this formula also contains Q. So in this case, Q is nothing but shear stress, and this is generated due to shear force or this is generated due to tension. So in this way we can calculate equivalent stress when we have shear and tension is present, or shear in as well as basically shear as well as compression is present. Now the question is how we calculate the equivalent stresses when we have bearing, shear as well as axial forces all are present in the belt. So this is what if we have bearing, shear as well as axial stresses present inside the belt. Code again gives some recommendation for finding the equivalent stresses. So the clause 10.5.10.2.2 says where bearing stresses FVR is combination with bending, that is due to either tensile forces or due to the compressive forces. FV and shear stresses Q under the most unfavorable condition of the loading in the butt belt. So this is related to the butt belt. The equivalent stress Fe is obtained from the following formula, and this should not exceed the value allowed for the parent metal. That is, it has to satisfy demand and capacity relationship. And the different terms in this expression is expressed here. So you see in this case Fe is the equivalent stress, and Fv, that is calculated as stress due to the bending, and this is in Newton per mm square, and FVR, that is calculated as stress due to bearing. So in this case this is due to bearing, and Q is the shear stress as given in Newton per millimeter square. So we discussed two situations. In one situation we have basically two forces, two kind of stresses that is present, shear as well as compression or shear and tension. In another situation we also have the bearing action, that is bearing, shear as well as axial forces are present. In that case how we calculate this equivalent stress, or we can also calculate the equivalent force if we multiply by the stress with the equivalent thickness or equivalent area, that is the throat thickness times the length, that is area. Now we will illustrate this how we calculate the equivalent stress inside the belt using an example. So let us illustrate using an example. So this example says we have a pipe of mean diameter 100 mm. So this is the pipe that we have, and this dimension is 100 mm, diameter is 100 mm. And the thickness of pipe is 2 mm. So this thickness that is given, and this is 2 mm. And this is connected to a gusset plate or thick plate that is 16 mm. So the thickness of this plate is given, and that is 16 mm. And we have to use fillet belt for this connection. So what we are doing is we are making a fillet belt at this point, and we are also making another fillet belt on this side. So basically if you see in circular, or if you see from this direction, you will have a circular area, and you are basically building all along the periphery of the circle. And it is subjected to a vertical force of 10 kilonewton at a distance of 0.5 m, that is 0.5 meter from the welded in. So this is the welded in, and from here at a distance of 0.5 meter, and there is a force of 10 kilonewton that is applied. It is also subjected to a factored twisting moment of 3 kilonewton meter. So we are applying another moment, and that is this one, and the magnitude of this moment is 3 kilonewton meter. So we have to find the size of the belt, assuming this is a soft welding, and a steel of the steel of plate or the gusset plate as well as the pipe that is used in this case is Fe410. So question is how we will find the size of the belt. So we have to consider all the stresses that is acting in this situation. So let us illustrate this. So this is the same diagram that is in the previous slide. So I have this pipe and this plate, and this moment is applied and this force is applied, and different dimensions is also written here. Now if you look from this side, this pipe, you will see the circular dimension. and the welding is done along the periphery. Something like this. Let's say T is the throat thickness of this weld. Now we have to find what are the stresses that will be generated inside this weld. So first stress, that is shear stress, that will be generated by vertical load, and in this case this is 10 kilonewton. So let's call this load as P, that is 10 kilonewton. Now if I consider a section that is passing through the belt and very close to the plate and pipe interface, and the section is shown here, if I consider the vertical equilibrium of this section, there has to be a force that is acting in the vertical direction, and the resultant of all this vertical force has to be equals to P. So these forces are acting in the vertical direction, and this will act all along, and the resultant of all these forces is basically equals to P. Now another shear stress that will be generated, this is because of twisting moment M, that is in this case M is equals to 3 kilonewton meter. So now if I consider rotational equilibrium of this pipe, and if we find what are the stresses that will be generated along the belt, we will see there is a tangential forces that will act along this belt at a tangential direction, and these forces are basically trying to prevent the rotation. So there will be a shear stress due to these forces. And finally we will also have the bending stresses due to load P. So if you see this load P, this is acting at a distance, so basically in this case this force is applying a moment, and this moment will try to generate a tensile stress on the top fiber and a compressive stress on the bottom fiber. So we have in this case three stresses. One is shear stress due to load P, another is shear stress due to twisting moment M, and bending stresses due to load P. So we have to find all these stresses, and then we have to find the equivalent stress. So let us find first stress, that is shear stress due to load P. So shear stress due to P, so these are acting in the vertical direction as I said earlier. So we have to calculate the magnitude of these forces or magnitude of this stress. So let's say shear stress due to load P is written as Q1. So we can write this is equals to force divided by area, and in this case this is the throat area, because the forces are taken by the belt and the effective area in case of belt is given by the throat thickness times the length of the belt. So we can write P divided by length is nothing but 2 pi r and throat thickness is T. And in this case R is basically, it should be outer radius, that is RO. But in our case this thickness is very small, that is only 2 mm. So we can say outer radius is approximately equals to the mean radius, that is RM, that is mean radius, and I can write this is equals to R. So outer radius is equals to the mean radius, and this is equals to R. So we can take this formulation. So if I plug all this value, so P is 10 kilonewton, and this divided by 2 pi, and R is 50 mm, and T is the throat thickness, that is unknown quantity in this case. So if I calculate this turns out to be 31.83 divided by T Newton per millimeter square. So this is the shear stress due to load P, and this is equals to Q1. Now let us calculate the shear stresses generated due to moment or the twisting moment T. So as I said earlier, these twisting moment will be perpendicular and this will act in a tangential direction and will have different direction at different point. If you remember mechanics of solid, we can basically calculate these shear stresses, and the formula for that is tau is equals to T divided by IP times R. So if we want to calculate shear stresses at this point, then you have to use this formula where T is the twisting moment, IP is the polar moment of inertia along a axis that is passing through the plane of this figure in this case, and R is basically distance from the center. This formulation is same as bending formula, that is bending stresses sigma is equals to M divided by I times Y. Only thing is, in place of M I have twisting moment I, and in place of I we have polar moment of inertia, and in place of Y we have radius R. Now let's say shear stress due to T is written as Q2. So we can write Q2 is nothing but T divided by IP in this case and multiplied by R. And the T value, the twisting moment is given, that is 3 kilonewton meter. So 3 into 10 to the power 3, and radius is 50 in this case. And I have to multiply by 10 to the power 3 to convert kilonewton into newton, and IP is nothing but 2 pi RQ times T. So if you remember how we calculate IP, so IP is nothing but integral R square dA. Now in this case R is constant, so we are assuming that this thickness is very small. So basically we are assuming that all the area is located at mean radius. So we can simply write R square integral dA, because R is constant. We are assuming because this is a very small tube, and dA is nothing but, you can find this area, that is 2 pi R times the throat thickness T. Now you have to remember that these forces are taken by the effective area of the belt, not the belt that is on the vertical plane. So this is the effective area, and that's why we are multiplying by the throat thickness. So if you see, IP is nothing but 2 pi RQ times T. Now I can plug the values. So 3 into 10 to the power 3 into 50 into 10 to the power 3. And this divided by 2 into pi, and radius is 50 mm and thickness is T. If I calculate all this, and this turns out to be, so 191 divided by T Newton per millimeter square. So now we have calculated shear stress due to vertical load P, that is direct shear. And we have also calculated shear stress due to twisting moment T. So we can now calculate the resultant shear stress. So let us calculate the resultant shear stress. So if I consider the direction of shear stress due to P, this is acting in the vertical direction and the magnitude is Q1. And this is acting at all places in the vertical direction, and the magnitude is Q1. Now similarly, if you consider the shear stress due to T, this is basically acting in the tangential direction. For example, at this place, this is acting in this direction and the magnitude is Q2. At this place, it is acting in this direction. And at this point this is acting in this direction, and at this point this is acting in this direction. So if you see, the angle between these two shear stresses are not same at all the points. For example, at this point this is 90 degree, at this point you can say 180 degree, at this point once again 90 degree, at this point 0 degree. So we can basically, for any given angle, for example, let's say I have shear stress Q1 and shear stress Q2 and the angle is theta, we can find the resultant shear stress Q, that is Q1 square plus Q2 square plus 2Q1 Q2 cos theta. Now if you consider maximum value of resultant shear stress, that will occur when cos theta is equals to 1, or in other words when theta is equals to 0 degree, and that maximum value will be simply Q1 square plus Q2 square plus 2Q1 Q2, and that is nothing but Q1 plus Q2. So this is the maximum shear stress that we'll have. So this is the maximum value. For design purpose, if I calculate the maximum value, that is enough, because if my building is safe for maximum applied load, then it will be safe at all the places. So we have to find the maximum resultant shear. So this will be, so these values are 31.83 divided by T, and this is 191 divided by T. So this value we have calculated earlier. So this turns out to be 229.83 divided by T Newton per millimeter square. Now we have calculated the shear stresses. We can calculate next, that is the tensile stresses or normal stresses due to bending. So let us calculate normal stress due to bending. So if you remember, we just discussed the direct shear stress is given by this formula, M by I times by. So this is same as sigma is equals to M by I times Y. So in place of sigma, we are writing Fa because the code uses symbol Fa. So this is M by I, and Y distance is basically the distance from center to the belt, that is the outer radius. In this case, this distance is R, and I is the moment of inertia about this axis. So how we can calculate this? If you remember, we can use perpendicular axis theorem in this case, because we know moment of inertia about a axis that is passing through this point and perpendicular to this plane, that is polar moment of inertia, that is equals to IP. So I can write IP is equals to I, that is moment of inertia about this axis, plus moment of inertia about this axis, that is also I. So I is equals to IP divided by 2. So if I plug this, I will have M divided by IP divided by 2, and this multiply by R. Now let us plug all this value. So moment is force times distance. Force is 10 kilonewton, and this force is applied at a distance of 0.5 meter. If you remember, in the beginning we said this force is applied at 0.5 meter, and let us convert this into millimeter, and the radius is 50 mm, and this divided by IP divided by 2, that is nothing but 2 pi RQ times T divided by 2. So this value will be 2 times pi times R is 50, and let us put throat thickness T and this divided by 2. So if I calculate all this value, this turns out to be 636.62 divided by T Newton per millimeter square. So this value is IP, not I. So now we have calculated normal stress due to bending, and also we have calculated shear stress. Once I know normal stress as well as shear stress, we can calculate the equivalent stress. And for this we will use the formula that is given in the IS 800, that is in the code. So let us calculate the equivalent stress. So if you remember, for the equivalent stress, code has the following formulation, that is Fe whole square plus 3Q square, and we have to take a root. So we calculated these values. Fe is 636.62 divided by T whole square, and plus 3 times Q is nothing but 229.83 divided by T whole square. So if you calculate this value, this will come 750.83 divided by T, and code says this value has to be less than Fu divided by root 3 gamma mW. That is, this value has to be less than Fu divided by root 3 gamma mW. So in our case, we have Fu value is 410 because this is a Fe 410 steel, and root 3, and gamma is 1.25. So we can calculate T value from this expression. So which turns out to be T is greater than 3.96 millimeter. In this case, T is basically throat thickness. So once I know the throat thickness, we can also calculate the belt size. And the belt size and throat thickness is related using this formula. In this case, is a constant, and if I have two plates that is perpendicular, or in other words, the joining faces are perpendicular, this value is 0.7. And we know T is equals to 3.96. So from here I can calculate S, that is 5.65 millimeter. So we can provide little bit higher side. So let's say we can provide a belt of size 6 mm. So if we provide a belt of size 6 mm, our connection will be safe. So to summarize, in this video we have seen how we can calculate the equivalent stress using IS 800, and we have also seen how we can calculate a stress for different cases. For example, if I have a force, if I have a moment, and if I have a twisting moment, and then we can calculate the resultant stress, and we can equate this with the formulation that is given in the code to calculate the belt size. So we can stop here and we will see more in the next video. Thank you.